All right, let's try to take a look at manually calculating the average and the standard deviation for these two sets of data. The average is a measurement of where is the midpoint of the data. So what's the typical data point? You can have mean, median, or mode as ways to express the typical data point. The average is also known as the mean. So the midpoint of the data taken by adding up all the data and then dividing by the number of measurements. So here we have two sets of data. Both of these sets of data are centered around, and they're evenly centered around 7.5. And so we're expecting the average for both of these sets of data to be 7.5 because it's evenly spread. This one's one lower, this one's one higher, this one's two lower, this one's two higher. So when you add these up and divide them by 5, you should get 7.5. The same thing applies to this set of data, but the difference with this set of data, even though we again have a midpoint of 7.5 and they're evenly spread, these are not spread as far. This is just half, 0.5 lower, 1 lower, 0.5 higher, 1 higher. So we have a tighter grouping of data, and that's going to show up in the standard deviation. We expect the standard deviation for this set of data to be larger because these data points are spread out more, and this standard deviation should be smaller. With these particular data points, it's kind of easy to see where the midpoint is and how this one is spread further than this is, but for other sets of data, it's maybe not as easy to see. And so calculating what the average and what the standard deviation are can let you know these things. So the formula for average maybe looks a little bit intimidating. This is the sum symbol, so that means we're going to add up a bunch of things going from I equals 1 up to I equals n. In this case, we have 5 measurements, so n would be 5. So we have, I wrote this on the side, measurement 1, measurement 2, measurement 3, measurement 4, measurement 5. And so we are going to add up these measurements, measurement 1, and then we add 1, we go to I equals 2, we add up measurement 2, I equals 3, we add up measurement 3, all the way until we get to the final measurement, which would be measurement 5, n would be 5. Let's put that, because we have 5 measurements. And then we divide that sum by 5. So this is what that looks like. Measurement 1, measurement 2, measurement 3, measurement 4, and measurement 5 added together in the numerator. The number 5 for the 5 measurements that we have in the denominator. So here I have added these up. They add up to 37.5. I wanted to take a brief moment to point out the significant digits of this operation for the average. All of these measurements are known 1 past the decimal. So when we add these up, we also know them to 1 past the decimal. So we have 37.5 with 3 significant digits in the numerator. 5 is exact. We know we have exactly 5 data points. We can count them. It's a counted number. So this is exact. We have 3 significant digits. We have an exact number with infinite significant digits. So we can actually be a little bit more sure of the average than we were of any of the measurements. So we have 3 significant digits in our average when we only had 2 significant digits in each of our measurements. So that's a little bit interesting. I guess we can say that if you're measuring something a whole bunch of times, it makes sense that you would be more sure of it than if you only measured it once. All right, so we have that average as 7.50. So let's go ahead and get the average of this second set of data. We have very similar results, and again, if you line these all up and down like I did for the previous set, you'll see that these are all known 1 past the decimal, and so our sum is known 1 past the decimal, and we can have 7.50 for the average of our second set of data as well. Okay, the formula for standard deviation is a little bit trickier, and especially from a significant digit standpoint, it tends to be a little bit of a hassle to follow it all the way through. So what we'll do for the standard deviation, especially with the square root and squaring things, for significant digits, what we'll do is just keep the same number of digits that we have in the average. So if your average, you figured out that you can take it 2 places past the decimal, then when we do our standard deviation, let's just keep that to the same place value, because having a standard deviation with 8 digits past the decimal is not really necessary if we're only dealing with averages that are 2 digits past the decimal. So let's keep this to the same place value as the average. So once we figure out our standard deviation, we'll keep all the digits in the calculator, and then we'll put the standard deviation to the same place as the average. We'll just keep it 2 places past the decimal. All right, so how do we actually calculate the standard deviation? This time we also have a sum. We are adding up from 1 to n, 5 in this case. What we're adding up here, instead of the measurements, we are adding up the measurement minus the mean, and then that difference squared. So let's write out what that looks like. And then in the denominator, n minus 1 is going to be 4 because n is 5. We have 5 measurements. So we have 4 in the denominator, and then we're going to take the square root of that whole thing. Okay, so here is that written out. We have measurement 1 minus the mean squared, measurement 2 minus the mean squared, and so on and so on. And then in the denominator, we have our 5 measurements minus 1. So here's what that looks like when we do the subtractions. We have a -2, a -1, 0, 1, and 2. Each of these differences has to be squared. So we have 4 plus 1 plus 0 plus 1 plus 4, which is 10. The denominator is 4. I guess technically we should keep this as 10.0 over 4. So we have the square root of 2.50, which is 1.58. So keeping 2 past the decimal to match the average, we'll report this as 1.58. Let's see if we can do the same thing for the second set of data. So here we have this second set of data. The differences between each measurement and the average are a little bit smaller. So we have a -1, a -0.5. Again, these are being squared, 0, 0.5, and 1. When we square these and add them up, it comes out to 2.5. 2.5 over 4 is 0.625. And then taking the square root of that result gives us 0.79. So let's get some room and write that. So this set of data has a standard deviation of 0.79, and it is smaller like we expected because each of these measurements is closer to the center point, the average measurement. So these differences are not as big. And so the standard deviation is not as big. So this calculation is a little bit cumbersome. It's good to know how to do it. It's in your note packet in section 1.5. I'm going to show you how to do it using a spreadsheet program because that's pretty fast and easy. So keep an eye out for that.